Welcome, and in this lesson, we're going to talk about Amazon EC2, which stands for Amazon Elastic Compute Cloud. So the focus of this lesson is to cover a lot of the core concepts needed when understanding and using Amazon EC2. After this video, we'll go in and start working hands-on in the EC2 environment as we reiterate the concepts that we learned in this video. So first, what is Amazon EC2? Essentially, EC2 are virtual servers in the cloud. EC2 is the instance computing platform for our individual servers. These servers or instances or virtual machines run software such as Linux or Windows. The service makes up of several different features. We have what's called the Elastic Load Balancer, which allows us to use round-robin load balancing between our instances in a single availability zone or in multiple availability zones. We have auto-scaling, which allows us to create elastic environments that can increase by firing up new instances to handle increases in demand based off of measurements like CPU utilization or network utilization. It also allows us to create self-healing environments. If an instance becomes unhealthy, it'll automatically replace itself. We can also use EBS volumes. EBS volumes are called Elastic Block Store and are network-attached storage volumes that attach inside of the operating system like a physical device would, but is actually stored over the network inside of an availability zone. And then, of course, we have our core EC2 instances. This is how we select the type of memory that we want to use, the type of CPU utilization, the type of network throughput we're working for. Now, there is a deprecated version of Amazon EC2. Now, for all new accounts before December 2013, this is depreciated, which means it's still available to you to use, but it's deprecated for all new accounts, which means it's no longer available for you to use. It is important to understand a few key concepts for EC2 Classic, and we will talk about those in this course. So please do not skip over EC2 Classic. So EC2 instances are made up of instance types. When it comes to designing applications, we need to determine what proper instance type we should use for our architecture. So instance types really describe the type of compute, network, memory, and virtualization architecture that our specific EC2 instance will run on. As an architect, we need to understand the proper instance type to handle our application load. If we want to run an application that, for example, uses auto-scaling, but we don't select the proper instance type, we don't want to run 20 T2 micros because we didn't select the proper instance type. We may only want to run 2 M1 smalls, for example. So T2 instance types are called what's considered burstable performance instances. They have a minimum CPU baseline performance that can be used. And what happens is when you're using less than the minimum, you are accruing what's called a credit. That credit allows you to burst past your minimum baseline CPU performance during times of high load. So the baseline of a T2 micro is something about, I think, 20% CPU utilization. But when you're using under 20% CPU utilization, you are accruing credits, which allows you to burst higher. So when it comes to architecting applications, if you have an application that's a production-ready application and requires high baseline CPU performance, a T2 is not for you. A T2 is for something like a dev instance or an instance that doesn't do much work most of the time, but every once in a while needs to do a little computing power. M3 instance really comes with a nice balance between CPU availability, memory, and network throughput. A C4 instance is considered compute optimized. It has a higher emphasis on our CPUs or virtual compute units. R2 instances have higher amounts of available memory. If your application is a memory hog, maybe a business intelligence application, for example, you might focus on the R2 instances. G2 is GPU optimized, which means we have strong GPU hardware available in it. L2 is called storage optimized. They're high I/O instances. So it includes high storage instances that provide very fast SSD-backed instant storage and it's optimized for high and a random I/O performance, and it's able to provide a high IOPS at a low cost. Our EBS volumes are network attached storage. So EBS optimized instances has higher network throughput to our EBS instances. So if we're doing a lot of input output operations against our attached EBS storage devices, and the amount of provisioned IOPS that we put towards it are not enough for our application, we might consider an EBS optimized instance. Now, one thing to remember is that EC2 instance sizes will vary in the amount of network capacity throughput, and it has other limitations such as the number of elastic network interfaces that you can attach to an instance. A larger size, remember we can have a T2 micro, a T2 small, a T2 medium, an M1 small, an M1 medium, an M1 large. These sizes greatly determine the amount of network throughput you have. So an M1 extra large has a higher network throughput than an M1 medium, for example. One thing to remember is that Amazon can phase out old generation instances per the SLA, and they will, but that's all because of innovation. So EC2 instance has two types of storage, and when we talk about this specific section here, I'm referring to the root device. So in Linux, you have your root volume, which contains kernel information, system information, libraries, commands, programs. And so what happens is we can choose to use our root volumes as either an instant store volume or an EBS-backed volume. An instant store volume is considered ephemeral data, which means the data on the volume only exists for the duration of the instance life. It's temporary data. That's what ephemeral means. So if we were to write information to an instance store backed instance on the root device, and we were to stop the instance and restart it, then that data would not exist when the instance starts again. Now this only applies when an instance is stopped or shut down. If we just reboot or restart an instance, the data is still maintained in its temporary volume. So one cool thing about an instant store volume is that it's a virtual storage device that has underlying hardware on the physical attached host that your instance is running on. This is different than an EBS volume. An EBS volume has network attached storage. It might be attached somewhere at the other side of the availability zone, which means it has to go over the open network, whereas an instant store volume is attached on the physical host, which means we'll probably get higher input-output activities and less latency when it comes to writing our data to the storage device. So that's a consideration in terms of performance and design architecture. Now, EBS-backed volumes are network-attached storage again, and that allows us to provide persistent data across EC2 instances. Because we can detach and attach volumes on the EC2 instance, and when the instance is shut down, that data is persistent because it's stored on an EBS volume. So what is an EBS volume? An EBS volume is network-attached storage to our EC2 instance. EBS volumes measure input-output operations inside of AWS in something called IOPS. IOPS are input-output operations per second. AWS measures IOPS as 256 kilobyte chunks or smaller. Operations that are greater than 256 kilobytes are separated into 256 kilobyte chunks. So for example, a 512 kilobyte operation, if you're reading or writing 512 kilobytes of data or more per second, would count as 2 IOPS. So if we have 2 IOPS and we have input-output operations per second, that is the equivalent of 1,000 kilobytes. What happens is we would be limited to a 512 kilobyte operation per second. So if we had 1,024 kilobyte operations, we would need to, in order to write 1,024 kilobytes per second or read, in order to have input-output operations in terms of 1,024 kilobytes per second, we would need to have 4 IOPS on the device. However, if we didn't, what would happen is those additional data chunks would be queued up for input-output operations, which could become a potential bottleneck. So the type of EBS volume you specify will greatly influence the input-output performance or IOPS your device will receive. It is important as architects to understand if our application requires more I/O to the EBS volume or not. So even volumes with provisioned IOPS may not produce the performance you expect. If this is the case, an EBS optimized instance is required, which prioritizes EBS traffic over the network, or you could also consider an instance with higher network traffic capacity. So there are three core volume types currently. We have the general purpose SSD, provisioned IOPS device, and what's called a magnetic device. So the general purpose SSD, which is commonly used as our root volume on a system, and is used in dev and test environments and smaller database instances. So how can we measure if we should use an SSD or a provisioned IOPS device? Well, a general purpose SSD has 3 IOPS per gigabyte. That's its baseline performance. If we are not using the baseline performance available, it can accrue some credits, which means it can burst past that. So the volume size of a general purpose SSD is 1 gigabyte to 16 terabytes, which is just over 17 terabytes. Now, considerations when using T2 instances with SSD root volumes includes our burstable versus baseline performance. So that burstable performance comes with our T2 micro instances versus just baseline performance on the other instance types. So if we had an EBS root volume with a root volume and 2 gigabytes in size, we would be able to have 6 concurrent IOPS operations per second. Now for provisioned IOPS, we should always use provisioned IOPS for mission critical applications that required sustained IOPS performance. These are examples of something like large database workloads. Now for provisioned IOPS, we can have a volume size of 4 gigabytes to 16 terabytes in size. Performs at provisioned level at all times and can provision up to 20,000 IOPS per volume. Now, magnetic is low-cost storage that we should not use in any production environment. So we use it on workloads where performance is not important or the data is infrequently accessed. And for a magnetic device, the volume size is 1 gigabyte to 16 terabytes in size. Amazon Web Services wipes the EBS volume or the underlying storage for an EBS volume with industry standard wiping techniques to ensure that your data or somebody else's data does not exist on the volume you provision. However, it does that when the first write or read operation occurs on the EBS volume. So when you first provision that EBS volume and you attach it to your instance and you have writing information to that volume, AWS will take a little bit of extra time to write that data because as it writes that data, it first erases whatever was on that specific block volume prior. So in order to get full performance out of an EBS, or I might add a brand new EBS volume, we should pre-warm the volume, which could mean writing zeros using the DD command to the entire block device one time after attaching it. Now this is again for the first input-output operations against the block volume. And we talk more about this in the SysOps course, but I feel it's important for everybody to be aware of the information while not having to completely understand the technical details for the CSA. Now, EBS snapshots. This is somewhat of a tough concept for students, so I would encourage you to pay attention. When it comes to backing up data on Amazon EC2, we should use EBS snapshots. EBS snapshots are available in Amazon EC2, but the underlying storage volume of an EBS snapshot is inside of Amazon S3 standard storage, which means our snapshots have 11.9's durability. Now, we can't just go to an S3 bucket and view our snapshots. We can access our snapshots in the snapshot section of EC2. But again, it's stored in the underlying S3 standard storage. So we have 11.9's durability. So a snapshot is considered incremental in nature. A snapshot only stores the changes since the most recent snapshot, so it reduces the costs, and you're only required to pay for that incremental change between snapshots. So, for example, when you create your first snapshot, all of that data is written to a single partition in the back end of Amazon Web Services. Now, let's say you write 20 files and you create a second snapshot. That second snapshot includes information for those 20 files, the incremental changes. The underlying data is still in that partition. That snapshot just writes that additional 20 files to that partition. What happens if we delete our very first EBS snapshot? The underlying partition of all of the data is still there, except we also have that 20 extra files that we've created. So if we restore from that second snapshot, we're going to restore to the point, it's a point in time snapshot, that has those 20 files plus all of the prior data. So when you delete your very first snapshot, you're not actually deleting all of the data, you're just deleting that snapshot in time. If we were to create yet another EBS snapshot that has an additional 20 files on it, and we deleted our second snapshot, we would still have all of the underlying data. We would just be restored to the point in time of that specific snapshot. So when you delete snapshots, you're not deleting your underlying storage. So this is where it becomes a little confusing when it comes to incremental changes. You're only paying for the incremental changes between snapshots. So the data is still available and you're only responsible for the incremental changes. So for each snapshot, let's say that your EBS volume is 20 gigabytes in size. Each snapshot is not going to be 20 gigabytes in size. Your first snapshot would have written 20 gigabytes in size to the underlying partition. Your second snapshot would write just that extra 20 files. So you're only charged for the extra 20 files. You're not charged for the 20 gigabytes plus the amount of size of those 20 files because the underlying 20 gigabytes is already there. So think about it like this. You have snapshots which are at point in time, but the actual source file is dynamically growing. If you delete an old snapshot, the data in the source location, our underlying partition, still exists. So frequent snapshots of your data helps us increase durability, right? So snapshots are stored on S3 standard storage class, but accessible only in EC2. The more snapshots we have, the more durable our data is. Now, when a snapshot is taken against an EBS volume, it can degrade the performance. So snapshots should occur during non-production or non-peak load hours. Now with EC2, we can have IAM access control policies that allow us to prevent what users can start, stop, and terminate instances. We can also have it down to the resource level, which means we can say that this user can start and stop this specific instance, and they can terminate this other specific instance. You can also say which IAM users or groups can access EC2. Now, while an instance is stopped, you are not paying for the compute time. You're only paying for the underlying storage on that specific instance or EBS volume. You can enable termination protection, which prevents somebody from accidentally sending an API call or inside the console from terminating an EC2 instance. We can even associate multi-factor authentication with the termination action for the API. So that way, if we want to prevent accidental terminations of EC2 instances or make sure only specific users can do it that have MFA on, that way there has to be that second authentication before the termination request is sent. Now we can control EC2 instances from the AWS command line interface or, of course, from the SDK. Now, one of the cool things about EC2 instances is something called bootstrapping. We use bootstrapping by sending a simple bash script to an instance only at creation time. Now, the cloud init program inside of the EC2 instance is what handles the user data. This user data, again, is just a simple bash script. So whenever we create an EC2 instance, we could pass it a script that just installs certain software or downloads the most recent version of your code from a Git repository. An instance's user or metadata is accessible inside of the specific EC2 instance. So you have to open this URL within the instance. And inside of a Linux instance, you would use curl. In every single instance, the IP address is the same, 169.254.169.254. Then you go to /latest/metadata or /latest/user data. So we can find out information like the instance's internal IP address, the instance type. There's a ton of information inside of the metadata about the instance. And so if we're writing a script where we need to determine the current internal IP address or other metadata about it, we can just make a curl request to this information. So let's say that we launched an EC2 instance inside the console and we said, let's launch 5 of these exact EC2 instances. Well, when that launches, it launches in what's called the AMI launch index. So it'll actually say which instance launches first. So we can use this in terms of creating automation, like if we're deploying out a master SQL server with replicated instances, right? So we could say the first instance inside of the index would be the master, and all other instances would be read replicas. So the Elastic Load Balancer allows us to round-robin load balance traffic across availability zones to instances. Now what this does is it creates high availability and fault tolerance. So if an instance becomes unavailable in one availability zone, the Elastic Load Balancer will automatically remove the instance from load balancing if the instance is unhealthy, and it will serve traffic to the remaining instances. Now, when we use it within a VPC, it can also act as an internal load balancer to load balance internal EC2 instances. So if we have a corporate environment that is connected a VPN to Amazon EC2 to run internal applications, we can still apply high availability and fault tolerance to those intranet applications with the Elastic Load Balancer. We can also create multi-tiered environments inside of AWS where we have our public-facing load balancer that accepts traffic and sends it to instances, where those instances then send traffic to an internal load balance for back-end application processing and then returns it. So again, the ELB automatically stops serving traffic to an instance when it becomes unhealthy. We can reduce the compute power of our CPU instances by applying the SSL certificate for HTTPS data transfer directly on the Elastic Load Balancer instead of on the EC2 instances themselves. Now, this is common practice inside of regular corporate and enterprise load balancers as well. So EC2 Classic, what we need to understand is this is still important. So a few differences with EC2 Classic is when you stop an EC2 Classic instance, the public IP address, the internal IP address, the private IP address, so in EC2 Classic, instances that are booted up are automatically assigned a public IP address. They are always public instances, and they always have a CNAME. They're never private instances. Each instance receives a private IP address. Again, a private instance is one that is not accessible to the open internet. And so we can't create subnets for an EC2 Classic instance. All we can do is start an EC2 Classic instance and access it through the public IP address provided. But each instance does receive a private IP address. The reason it receives a private IP address is because public IP addresses are routed through a NAT to an internal IP address. But this internal or private IP address is not part of a virtual private cloud. What this means is that if the instance is shut down in EC2 Classic, it will lose its private IP address and it will change on the next boot up. Now, since it will lose its private IP address and public IP addresses are associated to a private IP address network interface, then that also means when we stop an EC2 instance, that EC2 instance would lose its elastic IP address. When we started the EC2 instance again, we would have to reattach the elastic IP address. And we'll cover this later as we're going through the EC2 section hands-on. Security groups are used as a firewall in front of an EC2 instance. An EC2 instance can belong to multiple security groups, and security groups can reference themselves as source traffic and firewall rules. And we'll dive more into security groups as we go throughout the section. So that concludes it for this lesson. Go ahead and complete this lesson.